Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, so we're working on the JohnAudioTech collaboration where we're doing a power supply design. And it's going to be in two stages. The first stage is just to take the AC voltage and it'll work on a universal input, meaning, here in the US, 120 volts, 60 hertz, or somewhere else in the world, Europe maybe, where maybe you got 230, 240 volts at 50 hertz, okay? It'll work on any of these voltage ranges, and what it has to do first is convert the voltage to a DC voltage, okay, from AC to DC. So what we're going to do is we're going to use that PFC converter that we've already been talking about. Second stage, we're going to take that voltage, and by the way, we pump that voltage up to 400 volts. And the reason why is it's a boost converter. So even if you're putting in the high voltage AC, it still has to boost. So we just choose a voltage that's above the peak of that voltage range. That's why we come up 400 volts. And also, we don't want to use that voltage directly. We have to isolate it. So now we go through the second stage. And the second stage is going to have the isolation, first of all, and it's going to provide a plus minus voltage rail, okay, at the very least. And so we have to choose a converter for that. And one of the converters, because we're looking at doing 400 watts, it's kind of at the high-end threshold of this type of converter where you want to use it. But it's also a converter that's great because it takes the fewest amount of parts. It's very robust. It's a great converter. There's no, drawbacks other than it's kind of limited in power. It used to be said that people would say, oh, you can only use this converter for 100 or 200 watts. Well, that's not, I don't know if it was ever true. Anyway, it hasn't been true for a long time. You can go up to 400 watts. And here, let me just show you what we're going to do. We're going to do a forward converter, okay? So, what is a forward converter? I've got a bunch of stuff drawn on here. Just look at this blue part here first. What we're doing is we come in with our 400 volts, okay? We have a capacitor, and we have a transformer. This is our isolation, okay? And what a forward converter does is when the transistor turns on and it pulls current to that transformer, creates a voltage across this winding, it creates voltages across these windings. And when it creates those voltages, current flows. So when current's flowing to this side, it's also flowing to there. That's a forward converter. Now you may have heard of a flyback converter. We won't really talk a lot about that, but a flyback converter would be kind of the opposite. As current flows here, nothing's happening over here. It's storing energy, and then when it stops here, then it flies back and then the energy's dumped. That's a flyback. They're great for when you're doing high voltage or if you're just trying to make a really low cost power supply. But also, it's hard to make them up in the higher wattage, okay, because you have to store a lot of energy. So the part has to be pretty big. Where this is and so really that's an inductor. You're storing energy and then you're dumping. This is a true transformer, meaning that just like a 60 hertz or a 50 hertz transformer, you put AC on the front end, you get AC on the back end. As soon as voltage starts to develop across the windings, you're developing voltage across the secondary windings. Current's flowing primary side. This is the power side, the primary side, and the secondary side at the same time. That's a forward converter, okay? So it's a lot like your 60 or 50 hertz transformers, but we're switching a lot faster. So our transformer can be much smaller because, if we're switching at, say, 60 kilohertz, we're switching at 1,000 times faster than the 60 hertz. So the time that the voltage is on across the transformer winding, it's called a volt second thing. And the volt seconds, let's just say you multiply the volts to the seconds, the bigger that number is, the bigger this thing has to be. So if your seconds are small, your transformer is smaller, okay? So volt seconds. 60 hertz, 60 kilohertz, okay? A lot of times we're switching at around 100 to 200 kilohertz, and the reason why is 100 to 200 kilohertz, the parasitics, meaning the inductances in resistors or resistances in inductors and capacitors, you know, all those other things that just kind of come along for the ride. You know, like say in a resistor, say this is our sense resistor. He's sensing current going through here. There's going to be a little bit of inductance. Those are parasitics, things we don't want, but they're there. We can't get rid of them. When you're switching, say, from 60 kilohertz on up to 200 kilohertz, those things aren't unmanageable. They're easier to manage. And the balance, the trade-offs between the two parts of the switching cycle. There's the part where it's conduction, where this guy's on, you're just conducting. Now you're worried about DC resistance. And then there's the part where you're turning on or turning off, the switching cycle. And you get 2 of those switching cycles per cycle, right? On and then off. That's why often when you're looking at ripple, you'll see this ripple and then you'll see these spiky things. And those spiky things occur during the switching cycles, the time on and the time off. Because those sharp edges create spikes in those parasitics. So you can imagine, if you're, instead of switching at 200 kilohertz, if you're switching at 400 kilohertz, you're going to get a lot more of those spikes, you know, a lot more noise. So how do you stop that from happening? Well, this forward converter, I've really simplified the transformer winding. I'm showing 2 secondaries because we want 2 isolated secondaries. Now notice this. This is isolated from these because I'm showing that it's wound on a core. So that's what these are for. Okay, so it's a transformer wound on a core. But I've got 2 outputs here. It's not a split winding. It's actually 2 separate windings. It could be a split winding, but then I'd have to put the diodes in different places and that. What I'm trying to show here, though, is by illustrating it this way, I'm showing that you can put as many windings on this as you want. I mean, to a degree. But anyway, with 2 windings on the output, they can be identical. You can say this can be 35 volts, 55 volts. This can be 35 volts or 55 volts. So let's say we have we have 2 55 volt windings. If we tie the plus of this one to this one, if you imagine these are just like 2 batteries in series on the output, and the center part you're just gonna randomly call, oh, that's my reference, that's my ground. So put an S next to that for secondary ground. Okay, some people call that signal ground, but I believe in the early days P was used for primary side of the transformer, S was used for secondary side of the transformer. Okay, so if you want to call it signal ground, that's fine, but you know, it makes sense when you say secondary because you know that you're talking about a voltage that's isolated from the primary. So this is S for secondary, and we just put it here. We could have called any one of these things our reference because they're floating. Once we assign one as the reference, then every other voltage is going to be referenced from that, right? So if this is reference, and there's 55 volts across this winding, across this capacitor, and if this is a plus side, then this can be plus 55 in reference to this. Since we're taking the opposite side of this winding, this will be the minus 55 volts. So we got plus minus 55 volts in a reference. Okay, that's how it's just like on a 60 hertz on a toroid. You know, when you have those windings, whether it's a split winding, meaning you wind and you have an output, and then you continue winding, you have another output. Whether it's that way or actual separate windings on the output of a 60 hertz transformer, you kind of do the same thing, right? Well, not kind of, you do the same thing. It's just like an audio transformer that maybe you're familiar with, maybe you've used them before for your audio power supply designs. We treat it the same way with the switching power supply, okay? The capacitors are going to be smaller because we're filling them up 1,000 times or more a second than we would if it was 60 hertz or 50 hertz, right? And this is our rectifiers. So one thing that I should show you is we should get into the transformer a little bit more. But before we do that, I was trying to keep this drawing somewhat simplified but still show some detail. Over here we have the current sense resistor, so we have an RC filter coming off that. Just to, you know, that spike I was talking about on those edges, we want to filter that off, and we call that current sense. And this is our control chip, let's say. And the inputs to our control chip would be the current sense. We'd also have a voltage sense. That's what this little green line dotted thing is. It's coming down to a circuit that will have, that will be our feedback, okay? Our voltage feedback. And it'll go through an optical coupler. That's what I kind of tried to draw here. Those are little arrows showing the lights. The LED on this side. Transistor on this side. Transistor on this side has an A next to it. That's analog ground. And it's going to be, you know, we'll have, say, a 0 ohm resistor. We'll have the analog and primary ground tied together over here for our control chip. So A ground here. The reason I'm showing A ground is I just want to purposefully illustrate that we're using a quiet ground around our control chip. So the things that we don't want a lot of noise on, when we're switching, we can get some ground bumps, things like that, some heavy currents going through our parasitic elements like traces on the board. So what we try to do is the low current stuff, we try to keep it on the analog ground. And then we tie the analog ground to the primary ground, so there's reference to the same ground on this side, but we just don't want the heavy currents flowing through this quiet area, the area that we want sensitive circuits, okay? So we'll have our current sense coming back here, and we'll have our A ground on our current sense, and we'll have two lines, traces coming back into the circuit here. And our voltage feedback, same thing, we'll have A ground and our feedback, two lines coming back to our circuit here. And we'll run those two grounds together instead of doing a ground plane, because we want those currents to track each other so that they couple together, and yeah, we'll get a better signal that way. So, and then I'm just showing that A ground and P ground are actually the same reference. They're tied together over here. We will want to tie those together at a location where it's low impedance, where it's nice and quiet. So like, say, a bulk capacitor feeding this, maybe the bulk capacitor here, maybe those two things are close together, ideally. The trace, now, when you want to follow power current, the current loop for the power would be through here. From this capacitor, once we filled up with the PFC converter, then, so when this transistor turns on, when that current first starts to react to that, we want it to come from as close, we want the loop as small as possible, so we want something with low ESR that can, and low ESL, inductance, to react very quickly so we can keep those ground bumps from occurring, and we can keep those spikes as minimal as possible. So we want this, like this point and this point, actually to be tied very close together. We want the current to come off the capacitor through the transformer winding, through the transistor, current sense, and then right back to the capacitor. So that's our current loop, okay? Then we'll have another loop where the PFC is filling up this guy. So really, current will be coming from this, plus current will be coming from this. But the quicker current, you know, the quick reacting current for those sharp edges will come from this, and then he'll be supported by a bigger capacitor over here to kind of help keep that guy full, right? So just want to show that. And then let me kind of talk more about the transformer, okay? Let me draw some more stuff, because this is a Ford converter, but there's different types of Ford converters, okay? Let me show you another drawing. Alright guys, different types of Ford converters. Let's talk about it. Alright, here we go. Hopefully you can see this. No glare, all that stuff. Alright, so the typical Ford converter, this one right here. This one has what they call a tertiary winding, third winding, or a reset winding. And now I've shown the dots, the dot convention, you know, just showing that, hey, when current's flowing, this red one, transistor's on, it's flowing around here. The dot's on, okay, it's plus side of this winding, and it's the plus side of the secondary winding, and current's flowing out that way, okay? So your normal transformer for a Ford converter. I've done so many of these in the past, can't keep count. Done them for many years. Great converters, easy. you know, relatively easy to design, maybe because I've done so many of them, but very robust, and they just work. Reliable converters. Fairly low noise, but they're hard switchers, meaning they're on, they're off. You get those sharp edges, okay? Now, here's the thing with that, is let's say the duty cycle is on for 50% of the time. Well, the reason that reset winding there is it has to drain the energy from that transformer every time the transformer's off, okay? That way, well, let's say that didn't happen, there'd be a little bit of energy left on it, then you turn it on again, a little left energy on. Pretty soon, maybe after a few cycles, that thing would get saturated. The magnetic field would just build each time and finally saturate, okay? So that's why the reset winding. Dump the energy when you're not using it. And look, the arrow, the way you put that in there is you put the dot on the opposite side, so when the current's flowing this way, nothing's flowing that way because this is plus and it's against the cathode of the diode. So the diode has it turned off. When this guy turns off, then this becomes negative. The energy, the voltage instantly flips, right? It's that kickback energy you get on a coil. Well, when it does that, then this becomes plus, and now it can push current through that diode, okay? So it resets the transformer. Well, theoretically, you can have a bigger duty cycle than 50%, which is nice because if you have a voltage input that's changing and you have a turns ratio here, then you have to you know, compensate for the input voltage changing with duty cycle, right? And the thing is, you know, if you're limited to 50% duty cycle, then you can only go from, you know, like some say 10% duty cycle to 50%. And so it limits you on how much you can change your duty cycle. Well, the other thing is the nominal situation that you designed for is not going to be 50%, meaning that over on the secondary side, those two diodes I had shown before, if it were 50%, each diode would be on half the time. So you're kind of dividing up that energy between two diodes, which is great. But if you're not, then one of those diodes is going to be conducting a lot more than the other one. So it's just going to get hotter. So you can't distribute the temperature or the current, the power in your circuit the way you could if you could operate around 50% duty cycle. Well, most people when they design these forwards, you design them for just less than 50% because you have to have some off time, and so you know this guy's has to have enough time to reset. So if this is on say 47% time, then this guy might be on 47% time. So you have some off time, some switching time to let everything settle, okay? That's practically how I think most of these forward converters are designed. Now I say theoretically you can go more than 50% because you can, between turns ratios, you could have more energy in the coil to let the coil dump a lot of energy in a shorter amount of time. But I don't, you know, I rarely, well, I was going to say rarely, I don't know if I've ever seen an application note other than showing that theoretically that's possible. I don't know if, you know, let me know if any of you guys have ever done that before or if you've seen it done before. But anyway, it's rare, okay? Well, for years, I've been doing the active clamp forward converter. That's this situation. I'm going to explain the advantages of that. And I'll tell you what, when they first came out with control chips that would do that, I would ask the applications engineers that would tell me about this new chip, well, come on, what's the advantage? That's just so somebody doesn't have to design a transformer, because transformer design is not trivial. And some people are like, oh, just designing it with that extra winding, that's just one more thing I have to think about. And boy, it's neat that somebody came up with a chip that takes that you know, winding away from me, so now simplifies my transformer design. Well, no one really could explain the benefits until I started doing some simulations, and I thought, wow, look at this is awesome. I'll talk about that in a moment. I want to show you something real quick. Down here, might be kind of hard to see. down here, the transformer is right here in the middle, and there's a FET here. I'm showing the switches, you know, instead of a FET, just showing it's a FET turning on and off. But here you'd have two FETs. This is called a two-switch forward. So you have one on the bottom leg, just like this, but then you add one up here. And you turn them on and off together, simultaneously. And then you add these diodes. I'll talk about that in a second here. But the reason you would do this, the reason two transistors would, you know, come into play, is that now the voltage across the transistors is half. So if you have high voltage here, then say 400 volts, that could be considered high voltage. You know, today, FETs, transistors, you can easily get 600 volt FETs, no problem. So you don't need to do two transistors. If you're doing a higher voltage, then maybe you'd want to use two transistors so you can get better FETs. As the FETs have a higher voltage rating, the RDS on and other parameters like the capacitance of them, all that stuff starts blowing up. And so high voltage FETs aren't ideal for switching, especially switching fast or faster. So, you know, you would switch at 50, 60 kilohertz, maybe 80 kilohertz with designs, some of these designs that have higher voltage. Now, okay, now here's the diode. How do you reset this guy? Well, when it turns off, the energy on this side of the inductor gets transferred here. The energy on this side gets transferred down here. So you're constantly resetting this transformer, and these diodes clamp it to the rails so that, you know, you're always clamped to the rails, okay? All right, so that's the two switch forward. Just wanted to show you that because that's one of the forwards. I've worked with these from other designers where I've come in to kind of help solve some issues or whatever. Personally, I've never designed this kind. I really never saw the need. I could do the same thing with one transistor less, you know, with this, and actually one diode less too, by just having a winding put on a transformer. The FETs have always been good enough. So yeah, this one here, when I have seen it, it's by designers that haven't designed as many forward converters. I'm not saying that's not a good design. I'm just saying I just haven't seen it personally very much. Okay, and I haven't done it myself. Now, this one, the active clamp, what it does is active clamps, right? So you have your transformer, but then when this guy turns off, the energy, instead of kicking back here, you couple through a capacitor and you turn this switch on and drain it to ground that way, okay? This is called a low side. You can also do a high side. You can put the same configuration from capacitor to FET to the top of the winding to basically short out the transformer to the top rail. So you can do it either way. Usually you'll put it up here for higher voltages. We might just do that, okay? And you put it down here for lower voltages. Now, you know, we're going to do 400 volts here. You could do a, you know, from a 12 volt converter, you could design a transformer like this. Say a 24 volt system. Military has 28, 100 volts, 270 volts, or 400. Those are kind of the, I guess 48 and 72 volts, if I didn't mention those. Those would be a couple levels. So there's different levels that you could design for this. One of the cool things about the active clamp is this guy resets it quickly. So now you can go, gosh, you can go at least 70% duty cycle. What's nice about that is you can center the optimal, the nominal situation, the voltage, 400 volts, say your, you know, nominal voltage out, nominal, you know, you can set that at 50%. So nominally, whatever voltage you're expecting in your input, you can have the best efficiency and the best efficiency on your secondary side. Okay, so that's really cool. That's one of the really neat things. It also helps you design a better transformer because you can do that. So your transformer is more optimized. There's so many nice things about just getting that extra duty cycle. So the other thing about this is this guy right here, as he discharges, he can pull this pin down, and when this guy turns on the next time or he turns off, then he definitely can switch softer. So instead of being that hard switch, you get those sharp edges, you get a softer edge on this thing, and it just gives you lower noise. It's more EMI friendly. Now here's the other portion of that is on the if you looked at, say, the drain right here and why this guy's turning on and off, what you would see is you would see it step up. Gosh, let me draw that. I'll be right back. All right. See if you can see this waveform. I'm kind of running out. I need to get new markers. All right, guys. So here it is. Hopefully you can see this and everything, but the voltage would be, the transistor's on, right? So it's down. Turns off. It comes up and it overshoots. It has a spike up there, and there'd actually be a little bit of ringing, a little ripple there. And what that's caused by is that there's actually some leakage inductance in here, and that leakage inductance is this, okay? And then what happens is then it's flat. It might be flat a little bit longer depending on the load out here, and it's sending power out, okay? Because as this guy turns off, this one is, you know, it's still sending current over this way, and there's an inductor on the output, and it's transferring energy. And as it does, it's showing this flat wave, and then as that inductor runs out of energy, it's, you know, and it just kind of runs dry, what I call it, then you start to get this kind of oscillation. It's not, you know, it's not necessarily a bad thing. It's just running out of energy. Basically, it's just running dry, and it actually drops down a little bit lower than this level, and then you turn it on again, and then it repeats. Okay, and the off time would be equal to this at least, right? 50% duty cycle. That'd be over here. Okay, now this one looks different. You don't see that spike anymore because this guy's clamping it, and what happens is as this guy comes up, it actually, all this energy and everything, it actually is rounded. And so you take all that energy and you just kind of squish it down, it'd be that shape, okay? So take all that energy and basically average it. And so you get this nice kind of rounded top end. And so you can see that it's softer switching on the top and it's softer at the bottom. It just much better signal over here. So the voltage over here is going to go up 2x plus this, and say maybe 20% from that spike, 10% at least. The reason it's twice is, remember, you had 400 volts, right? And then what happened is when that transistor turned off, then the voltage flipped over, so now you have 400 volts across here, plus 400 here, plus the 400 here, so now you have 800 volts on that drain, so it shoots up twice, but then you have a little bit more voltage. So I think I said 600 volt transistors before, but you know, 1000 volt transistors are easy to get. But anyway, so then you end up with a high voltage transistor for this situation because the voltage, because you're dealing with this, okay? Now over here with the active clamp, it's more of a rounded voltage, so you don't get that spike, you don't get it jumping up 2x quite. It's more, it's less, and so you get less voltage stress on your transistor and on everything else. So it's just a lot cleaner, lot lower noise operation. So we like it. Active clamp, way to go. Done a bunch of them, and they're very robust. They're very reliable, and yeah, I use them in a lot of military stuff. These got the 4 converters, active 4, you know. Now, I did a design for space, and I wanted to do this. I wasn't able to because I couldn't find a controller at that time, and to do it without a controller is a little more complicated. So this kind of design is used in space a lot. It's very common design for space applications. Alright guys, so hope you like that. That was kind of an intro to the next stage of our design. And we're going to crank to this active clamp forward. And the cool thing about the forward converter is very straightforward. Anyway, it's I think it'll be somewhat easy for you to understand. You know, you got your buck converters, your boost converters, and then you have those DC-DC converters. Sometimes are easier to understand, well, often, than isolated converters. When you have isolation and transformer design, it complicates things. You have the feedback loop that has to be optical. Well, it doesn't have to be optically coupled, but it has to be isolated. Very common it was optical. And maybe we'll use, you know what, maybe in this one we'll use a magnetic feedback. I've been doing that a lot lately too, and those are really cool for different reasons, and we'll talk about that when we get there. But anyway, yeah, isolated converters can be more complex because of the feedback control. It has to be dialed in a little bit better. And, you know, with the boost and the buck, a little bit more difficult to have those guys go crazy on you because the feedback loop goes unstable. With the isolated converter, yeah, it's that can happen. So it takes a little bit more finesse, let's say, to get everything to work right. But it's not difficult. It's the KISS method, right? We're going to show you how to do it. So thanks for watching. 2 thumbs up to my patrons as always. And also to you guys that hit that thank you button down below. It's next to the thumbs up button. So free way to help the channel, hit that thumbs up. Hey, subscribe if you haven't done so. I get a lot of comments from guys that have been with me for some time, but you're not subscribers. It'd help out the channel if you subscribe. But anyway, I appreciate you watching videos either way, and thanks for being here. And let me know what you guys think. Give your comments down below. That's a great way to support things too. The YouTube analytics likes those like things and the comments and all that stuff. So, alright guys, I'm going to try to get another video out this weekend, but let me know what you think of this one. Alright, thanks for watching. We'll see you next time.